theorems that are created from chords. So our first theorem that we're going to talk about today is if you have two chords going through a circle, these chords are, the chord lengths are proportional to each other from their intersection point. So if you take each half of that chord and multiply it by the other half, set that equal to each half of the other chord multiplied together, they will be equal to each other. So that means CA times AD will be equal to BA times AE. Each half of that same line segment multiplied by the other one will be set equal to the other one. So it's a little bit confusing at first, but when we start talking about, or when we start doing it, it's actually pretty simple, pretty easy to work with. We're dealing with a lot of multiplication today. So if you were to use this to solve, all you have to do is take, okay, look at your line. So I have a line 4 and 6. So I'm going to take each half of that line and multiply it together. So 4 times 6. I'm going to set that equal to the other line with each half multiplied by itself. So that's 8 times x. That'll give me 8x. So I have 4 times 6 equals 8 times x. If I simplify this, this is 24 equals 8x. And then all I have to do is divide by 8. And x equals 3. And that would be my solution. So once again, you just take each half of the lines, multiply them together, set it equal to the other half of the line, multiplied together. Think you can try that second one? Or do you want to do that second example? What are each half of your lines if you need a little? So if we set that up, what did you end up with setting up that second one? Yeah. 6 times 3. Set that equals to 2 times x.
6 times 3 equals 2 times x.
So 6 times 3 is 18. 2 times x is 2x. Divide by 2. X equals 9. Pretty simple? Yes, no? Okay. What's different about that third problem? One has an expression in it, and that x minus 5 rather than just a single variable. How would you set this up?
4 multiplied by x minus 5 equals 2 times 6.
So I can just write it like that?
Did you guys correct? Yeah, we have to, yeah.
Good, because we're multiplying the whole thing of x minus 5. Remember to put this parentheses around it. How would I simplify this to solve? What would I need to do? Distribute. Good. So we can multiply 4 times x, which is 4x, and 4 times negative 5, which is negative 20. And then 2 times 6 is just 12. And then from here, two-step equation, add 20, 4x equals 32. Divide by 4. Divide by 4. X equals 8. I'm pretty sure half of my solutions on the whole thing except for 8. Doesn't matter important. It's just if you could guess what x equals, it's probably equal. What about that next one? What's different about that? Every single piece has an x in it. We can still set this up though. It'll look pretty intimidating, but we can set it up. So we take each half, so x is 1 half, then the other half would be x plus 6. So that equal to the other halves times each other. So x plus 4 times x plus 1. So because we change everything to expressions rather than actual numbers, it's a little bit harder. We have a lot of variables to deal with. Can we still simplify this?
Mm-hmm.
So how can we simplify this, the left side? So we can distribute that x. And what's x times x?
X squared.
Okay, x squared. And then 6 times x will be 6x. How can I simplify that right side? Because I have x plus 4 times x plus 1, both in parentheses. did this a little bit last year. Actually, the Algebra 1 students this year are learning today. How can we simplify this?
I remember. Okay, on the words was polynomials. It's simple.
So with this, we had a little mnemonic device when we were multiplying two binomials. We called it foiling, which was your first, outer, inner, last. So we took each of those terms. So you took x, times it by the other x, then x, times it by 1. 4 times by x, 4 times by 1. You took each piece of that first parentheses and you multiplied it into each piece of the second half. So x times x gave us x squared. X times 1 gives you 1x. 4 times x gives you 4x. And then 4 times 1 is 4.
Isn't x squared equal to x?
No. X squared is x times x. 2x is x plus x.
I'm a little.
It's okay. Do we have any like terms?
1x and 4.
1x and 4 are on the same side. We can simplify that. Good. We have x squared plus 6x equals x squared. 1x plus 4x will give you 5x plus 4. Why isn't x squared and 6x like terms? Good. Whenever you're looking at like terms, you always still need to remember exponents. So exponents separate which terms are like terms. Good. Okay. What can I do? Inverse what? Okay, inverse my 5x. So it'll be like terms into 6x. So that's x squared. 6x minus 5x is just a single x equals x squared plus 4. Okay. Any other like terms? X squared and x squared. So if I subtract x squared, that cancels out. If I subtract x squared, that cancels out. So both my x squareds cancel out. So all I'm left with is just x equals 4. That's my solution. So even though it seemed pretty intimidating, even though we had a lot of variables, everything canceled out and it was fine. We didn't have to worry about dealing with any x squared or anything like that. But remember, anytime you have a binomial, a two-term times a two-term expression, we can multiply each piece by each other. We call that foiling from last year, which was first, outer, inner, last. All right, if you flip over, we have two other theorems. I honestly have not seen these theorems show up on the state test in the past. It doesn't mean they can't show up, but I find them less likely to show up. They're not as used as common, and so it's possible. I still want you to learn about them just to be familiar with them, but I don't find them as something that will be super in-depth shown. Basically, what the first one is you have two chords crossing through a circle. As long as those chords are the same length, the arcs intercepted by those chords will be the same arc measure. So if you have both these chords, A, B, and C, B are the same length, that means 100 and 100 will have to be the same. So it's pretty simple, pretty easy to learn. The other one's a little bit harder, a little bit more complicated, not too much. If you have a diameter, and then a chord that's perpendicular to that diameter, anywhere through your circle, that diameter will automatically bisect your chord in half. It'll become a perpendicular bisector, and each half of that chord will be equal to each other. So it's any chord perpendicular to a diameter will always be bisected in half. It doesn't matter where the chord is along the circle, as long as it's perpendicular. Are we okay with that? Once again, these theorems, I haven't seen them show up as often, having to know these ones, but I still want you to just become familiar with them just in case something shows up and you need to use them. I believe the next slide, or the next two problems on your paper, I skipped on accident on the slides. So the next one is, what is the measure of arc BC? And it has your circle, and it has BC with the arc on it, and then it has AB with the 120 on the outside. What do we learn about the arc of BC? How can we figure that out?
They would be the same, maybe of the same length and the arcs are the same.
So if our chords are the same length, then the arcs are the same, and we have those little dashes, so we know they're the same. So the arc of BC would just be 120 as well. Good. What about the value of x for that second one?
10.
10. We know as long as the diameter is perpendicular to the chord, it bisects it. So one half of that chord has to be the same half or equal to the same length as the other half. So one's 10, the other's 10. Okay. So sorry, I didn't have a slide for that. I don't know. I just must have skipped over on accident. What about that next one? What is the value of x? We have 10x plus 2 and it is plus 18. What can we do with this? Why do you think you use something equal to each other?
If the diameter like perpendicular will be, intersects the chord.
So our chord is perpendicular to our diameter, so both of these have to be equal. And if both these chords are equal, we know the arcs of the chords have to be equal. And so that means 10x plus 2, 10x plus 2, not 10x squared, equals 8x plus 18. And from here, simple multi-step equation, get all your x's on the same side, get all your constants on the other. Whatever. The 2x plus 2 equals 18, minus 2, 2x equals 16, divided by 2, 2x equals 8, once again. What about that second one? 7 equal? Why can't you set them equal? Why can't we? Diameter bisects your chord, once again, because it's perpendicular, so each half will have to be equal again. So that means that the number 4x minus 5 equals 2x plus 1. From there, once again, another two multi-step equations, subtract 2x, we have 2x minus 5 equals 1, add 5, and we get 2x equals 6, divided by 2, and x equals 3. Once again, I haven't really seen these show up as frequently on the state test as other questions that might show up, but I still just want you to be prepared just in case. Are we okay with that? We have two other theorems we're going to talk about. They're very, very similar to each other, and they are the same theorem. They're just a little bit different. This first one, what this is saying, it's called the segments of a secant theorem. A secant line, just like we had a tangent line, is a line that goes and touches your circle once. A secant line is a line that passes through your circle and creates a chord on the inside. That's a secant line. Just funny names that we have. So if you have two lines like this, what we've learned is if you take the outside of that line, multiply it by the entire length of the line, that will be equal to the other outside times the whole length. The thing is, we'll want to remember it's the whole length, not just the inside piece, but the whole line. So it's the outside times the whole thing, outside times the whole thing. Those will always be equal to each other. So if we look at an example of this, it's the outside times the whole length. So looking at my first line on top, I have my outside length is 9. What's the full length of that line? So 11 is the inside piece, but what's this entire length of EB? 20. So we can just take 9 plus 11, and we get 20. So the outside times the full length, that will be equal to the outside of the full length times for my other one. So that means 10 is my outside. What's the full length of my EG? This one? They're proportional, not necessarily equal though. How do we find the full length of this line? How do we end up with 20? Okay. We add these together, what do we get? Not 10x, that would be multiplying. It would be 10 plus x or x plus 10. So we're going to create a little expression by adding those two together. We don't know what x is yet, so we'll have to leave it like that. But that's fine. We know how to simplify this. We know how to solve this. What would you do first? 9 times 20, that should give us 180. And then with this side, we can distribute in. So that's 10x plus 10 times 10 is 100. And then from there, two-step equation. That's 80 plus x divided by 10, 10, and x equals 8. Okay with that? Just once again, outside times the full length. Outside times the full. Do you think you can get the second one? Good. Or do you want to do that one together? Do that one together? Okay. So once again, it's the outside times the full length. So looking at my top line, the outside is 6 times the full length of that line. So it's 6 plus 9, which would be 15. This is going to be equal to the outside times the full length. So my outside for my bottom line is 5. The entire length of that is going to be x plus 5. Are we okay with where I pulled these numbers from? And then from there, once again, distributing, multiplying. 6 times 15 is 90. And you think about it, yeah, you can think about it like 6 times 5 is 30, and then you have 3 groups of 5. 5 times 5x plus 5 would be 5x plus 25. You distribute that in there. And then always do equation. You're probably getting bored. 2-step equations. So we get 5x equals, I think that's 65, divided by 5, x equals 13. Are we okay with that? Try the third one then, on your own. Not that one. Yeah, we should have done x equals 4. Let's see what we did. Alright, so we had, oh, so you multiply these for this full length? We want to add them, so it would be 6 times 16. That's a circle mistake. So we should get x equals 4. What is different about this fourth one compared to the rest of them?
X is on the right and looking on the front.
Instead of our x being the inside, instead of the x being the chord length, our x is on the outside of the line. So let's see how that will change the problem. So typically, or we always use the outside times the full length. So the first one should be 5 times the full length of that line, which is 12. This is going to be equal to the outside, which is x, times the full length of that line, which is x plus 4. Okay. So rather than having a number outside to distribute in, we have a variable. So that might change this a little bit. So 5 times 12 is 60. We distribute this x in here. What's x times x?
X squared.
And then x times 4?
4x.
4x. Okay. What like terms do we have?
No.
What do you mean?
You can't.
None of them are like terms?
You can't combine your x squared.
Huh. What can we do?
Can we divide it or something? Or square root everything? Yeah.
So if we square root,
We can't square root 4x, can we?
if we square root this whole side, we'd have to square root 4x, but that would give us a square root of x. In order to get rid of the square root of x, we'd have to square it. But then we have to square this again. That would just bring it right back in the same circle. So it'd be like a big loop of getting the square root versus a square, and square root versus a square. So it won't get us there. Right?
What do you mean this problem?
No. Squaring it would just give us even more stuff to deal with.
Wait, what if we divide it by x?
Divided by x, but then we get x on the other side of the equation. So it might simplify one side, but now we're adding another x into the problem.
Then we'll be like, then we get a line term. We just leave it.
Just give up.
Yeah.
I'm going to change it a little bit. I'm going to move this 60 over to this side.
Oh,
What's 60 minus 60?
0.
Okay. So I have 0 on one side of mine equals. So
I didn't even know you could do that.
equals 1. 0 is the number. So 0 equals x squared plus 4x minus 60.
Plug it in. What is this? You just have to add the 60 back over. Charles, what do you do?
What is this?
Oh, what's that thing? Not unequivalent, and no name.
What do we call a function that has an x
Not a
squared?
function. X squared.
Something we dealt with a lot last year. Algebra 1.
Are those chemical functions? No. Chemical. No, there's something like weird.
It was a quadratic.
Oh, my word.
So quadratics were any functions that had a degree of, or any polynomial that had a degree 2. So it had an x squared. Or always had that square.
Okay.
How did we solve quadratics?
Oh, quadratic formula.
Quadratic formula. What's a quadratic formula?
Opposite of b minus square root of b squared minus 4ac all over 2a.
Opposite of b plus minus square root of b squared minus 4ac.
Only thing I remember
Okay.
that y equals mx plus b. That I swear those are the only equations I know. I don't even know the 4. But I think one's for slope. Yeah, y equals mx plus b is slope.
So,
last
last year we learned if you have a quadratic that's equal to 0, everything's on one side, 0's on the other, you can use the quadratic formula to solve. You have to figure out what your a, your b, and your c were by looking at, okay, what's the value in front of the x squared, what's the value in front of the 4, or the x, what's the value, that's my constant. That was your a, b, and c. We plugged all of those into your quadratic formula, and then from there you could use your quadratic formula to solve.
really have to do that?
We're not actually going to go through the whole thing. I just want to remind you. Another thing you could do is you could also do complete the square. We could also do, what else? Factoring. Those were 3 methods we had learned last year, I think. I think those are the only 3.
I remember.
Yeah.
That was like the one that people
So, quadratic formula, don't forget it. It still shows up sometimes, even when you have things like this.
You made it show up. Yeah, I'm crying.
I actually didn't think this problem. But we're not going to worry about going through the quadratic formula. I just want to throw that out there just to remind you. All right. This next theorem, this last one we're going to talk about, it's very, very similar to the one we just talked about. Ladies, okay?
Yeah.
This theorem is very, very similar to the one we just talked about. What's different about it, though?
The one that touches an outside point. There is no number.
What do we call a line that touches the outside? Inscribe is a shape on the inside. What do we call a line that just touches the outside of a circle?
Radius? No. Tangent line.
We learned it. Yeah, tangent line. Inscribed is when you have a shape on the inside and it touches, each point touches the edge. Or no, inscribed, I'm sorry, is where you have a shape and you have a circle on the inside that touches each edge, which all of those edges are tangent lines of the circle. But our tangent line is just a single line that goes along and touches that one single. So yes, you were correct in a sense. So rather than having 2 lines that just pass through your circle like we did with this one, we now have 1 line that passes through your circle.
And one doesn't.
And one that just touches the outside. Thing is, our last one we saw is we took the short length of the line and multiplied it by that entire length. And so that's still the same. Short length times the entire length. What's the short outside piece of this one, though? What's the entire length of the line?
Yeah,
So if I multiply those together, what would I get?
something out of school.
So let's say it was x. So I would take the outside length times the entire length, which would just be x times x, which is
X
x squared. So it's the same idea on the exact same problem we are just doing. The exact same formula. The only difference is the entire line is outside. And so the entire outside piece is the entire line. And so you're just squaring that one piece, but it's really the exact same stuff we were just doing in those same problems. It's just slightly different. We just need to think about it.
So x equals x.
It would be x times x, which gives you x squared, and then whatever these ones are. I was just throwing in a value for that.
So anytime you see like the going next time you see like there's like an x, it's always going to be x squared.
As long as the x is on the outside piece. So we know, because this is a tangent line, I square that line. So it's x, so I'm going to square it. And the other one will still be the same. It's the outside piece times the entire length. So this entire length is 16. And then we'd solve from there. 9 times 16 is 144. And then from here, we just take the square root, get x by itself. And it's x equals 12 is your solution. Man, and it's freaking out, yeah. Are we okay with that one?
Mm-hmm.
Think you can get that next one? Give it a try. So for that one, we should have gotten x squared is the outside length. That's equal to 4 times the entire length of my line, which is 4 plus 12, which is 16. X squared, this is x squared. 4 times 16 is 64. Square root of 64 is just our favorite number that we keep getting.
8.
What's different about this one?
Your x is one.
So our x is no longer the tangent line, it's that inside piece. But we can still set this up. We know it's our tangent line squared, so 24 squared. Give us a big number. That's equal to the outside of 12 times the entire length or times the whole length. So that's 12 plus x. 24 squared, probably need a calculator on that one. 24 squared gives us, I think it's 150 or 576. Yeah. So it's 576 is equal to, distribute our 12s in there. 12 times 12 is 144. 12 times x is 12x. So in order to get x by itself, you need to inverse our 144. 576 minus 144 is 432. That's equal to 12x. Then divide by 12. And to give us our x. So 432 divided by 12 is 36. X equals 36. Big number. Are we okay with that one? And then what's intimidating about that last problem?
I see it.
You have to square it even though it's already square.
So the square, our tangent line is square root of 3. So we have to square that, and then that's times x, and then sorry. So it's x times 2 plus x. Square root of 3, or square root of 3 squared. What do we know about square roots and squares? They're opposites. So what's going to happen?
They cancel each other out.
They cancel each other out. So I'm just left with the number on the inside. Just left with 3 equals, and then we can distribute that inside. That's 2x, and x times x is x squared. Once again, we're set up in one of those situations where we don't have any like terms. We have a constant, we have an x, and we have an x squared. So in order to solve this, we would have to inverse our 3, rewrite it so we have it in standard form. So it's 0 equals x squared plus 2x minus 3.
This is that one.
And then we'd have to quadratic formula, complete the square, factoring whatever option you figure out. So, cool. Another fun, jolly old time. And there's one other thing on your paper. We don't have any problems about it or anything like that. But we started off with what happens if you have two lines. What do we know about the lengths of two lines? Then we started, okay, what do you know about the length of a line and a tangent line? Now we're going to look at what happens if we have two tangent lines. What do you notice?
They're the same.
They're always equal to each other. The two tangent lines will always be the same length from their intersection point to where they cross out a circle.
Will ever be the same where they're not?
No. As long as it's from the intersection point to where they cross the circle, they will always, 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 always equal the same. That's what a theorem is. It's true as long as they meet these criteria. And that's where we'll call it for that. So I know this was a lot that we went over and a lot of stuff that we talked about, but we'll have some time to practice tomorrow, to review, to sort of work through some of these. A lot of these theorems are pretty similar to each other, so if we stick with that, it shouldn't be too